Okay, I thought I might provide a little bit of guidance for the lab that you're working on Thursday and Friday. Oh, tea. All right, Part A in the lab references L6, R6, and M6. And you need to be aware, if that's unclear, that that is a left sum, an LRAM, with 6 rectangles. R6 is a right sum, or an RRAM, with 6 rectangles. And M6 is a midpoint sum with 6 rectangles. And they give some instruction in the lab as to how to calculate the LRAM, RRAM, and MRAM. But that is just another version of the method that we've already discussed. So you use whatever method you prefer to come up with your rectangular sums. It also says draw a sketch, but you should just use the sketch that's given. There's a sketch on the front page for L6, and then on the second page for R6 and M6. So no need to redraw the function. Please remember that you're using the function 9 minus x squared for all 3 of those. All right, Part B. In this one, what you are doing is using the rule of 3, which means you're going to look at this problem graphically, analytically, and numerically. So what we are talking about is the definite integral from -1 to x of t dt on the interval from -1 to x, obviously. And Part A says to fill in this table. And I want to clarify, you should read Part B before you continue listening to my directions so they become more clear. But when you're filling in the table, you're actually plugging the x value into your definite integral. So when you are finding a of x when x is 0, you're doing the definite integral from -1 to 0 of t dt and find that value. And you're supposed to use fn int on your calculator to do that. And then when you are finding a of 1, you're doing the definite integral from -1 to 1 of t dt. I should make clear this is the problem that I'm doing is number 5 on this page, which is one of the 2 that you have to do. All right, so you will fill in the table using fn int and plugging into the definite integral. Then Part B just wants you to plot that data using your calculator. It says to use stat plot and to put x is in L1 and a of x is in L2 and to graph the data. In this case, not in every case, but in this case it comes out to be a parabola because the antiderivative of t is t squared over 2. So you can use a quadratic regression on your calculator, and you can find that under Stat Calc. All right, so that is the first method. We've numerically found the definite integral from -1 to x of f of t dt when f of t is t. So that's the first method. The second method starts in step D. It asks you to graph y equals f of t, which in this case, for number 5, that's the function y equals t. So you are graphing the line y equals t, which is the same as the line y equals x that you're used to seeing. And then you'll use the triangles to find the area under the curve from -1 to x. So this is graphically finding the area under the curve from -1 to x. So the answer we get from this using geometry will be the second time, or the second method of finding what we are looking for here. And then finally in Part E, you're asked to use the definition of a definite integral, which means use fundamental theorem of calculus, which is the definite integral from a to b of f of x dx is equal to the antiderivative of f evaluated at b and a, and you subtract. And so this would be the third way that you find the definite integral from -1 to x of t dt. So hopefully that helps clarify things a little bit. Now let's look at the next part, Part C. In this one, we call this Fundamental Theorem Part 2. And what we find out is that the derivative with respect to x of the definite integral from a constant, this a is a constant, to x of f of t dt, well, the derivative simply undoes the definite integral, and the answer is just f of x. So, for example, if I were doing the derivative with respect to x of the definite integral from 1 to x of tan squared t times sine t dt. Looks like a very involved definite integral, but because we're doing the derivative of that definite integral and we're going from a constant to x, the solution is just the integrand in terms of x, tan squared x times sine x. So it is this function evaluated at that variable. All right, so what we have to realize is that if we have an integral that goes from a constant to some function of x other than just x, we are going to need to apply the chain rule. So if the derivative, if we're asked to find the derivative with respect to x from 1 to x cubed of t squared plus t dt, well, we're still doing the derivative of the definite integral from a constant to some function of x. Well, it will still be this function evaluated at that function of x. So that's where we get x cubed squared plus x cubed times, this is where we need the chain rule. Since this is not simply x over here, we need to apply the chain rule, which is the derivative of the inside, which would be 3x squared. So this example is not, these two examples are not on the lab, but they are to help you do the last page before the derivatives on the lab. And I have given some guidance on number 3. And so take a look at this problem. We're doing the derivative with respect to x of the definite integral from x squared plus x to sine x of the function cube root of t plus t to the fourth. So I'm going to say, to help us a little bit on this one, let's just call the cube root of t plus t to the fourth, let's just call that f of t. So the first thing we would do if we wanted to work from the inside to the outside of this composition function, then we would take the antiderivative of f, which you'll see right here is capital F of t, evaluated between x squared plus x to sine x. So the next thing we do is we evaluate capital F at sine x minus capital F of x squared plus x. And then we are asked to take the derivative with respect to x. So we get capital F prime of sine x, but because the inside is not simply x, we need to apply chain rule, so we have to multiply by cosine x, minus capital F prime of x squared plus x, and again, because that is not simply x, we need to apply the chain rule, which is 2x plus 1. So then we need to remember that capital F prime is simply f. That is the derivative of the antiderivative. They undo each other, and you're back to lowercase f. And lowercase f from the very beginning, we said, was the cube root of t plus t to the fourth. So to write our final answer, we need f of sine x, which would be the cube root of sine x plus sine x to the fourth, times the derivative of the inside, which is cosine x, minus capital F prime, which is f of x squared plus x. So we get the cube root of x squared plus x. These should be x's. There we go. Plus x squared plus x to the fourth. And then times the derivative of the inside, which is 2x plus 1. So hopefully this helps you finish up the last page of the FTC lab, which is actually the page before your page of practice derivatives. Remember, this whole lab is due December 1st, and I hope you all have a wonderful break, and happy Thanksgiving.